Okay, so what we will do is we'll talk about, well, we'll start chapter 8. Chapter 8 is to me, it's a very interesting chapter. Chapter 7 talked about electrodynamics, right? We talked about the complete set of Maxwell's equations. Now we've talked about the energy contained in the electromagnetic field, right? E squared and B squared, 1/2 E squared, 1/2 B squared. There's an epsilon naught mu zero somewhere over there. But this takes it a lot further. We'll talk about the energy, the momentum contained in the field, the conservation of energy and momentum. We'll also talk about, we'll use tensors, so you get to see tensors for the first time in this class. I know you've seen that in classical mechanics. And the whole balance of electrodynamics will be considered in this chapter. So again, just to be consistent with the book, I want to recall a few of the things that we have seen before. So divergence of E is rho over epsilon naught. And then curl of E is minus dB dt. Divergence of B is 0. Curl of B is mu 0 J plus mu 0 epsilon naught dE dt. This was the displacement current that we added towards the end. Remember, if you have a single charge, a charge in an electric field feels a force due to both the electric and magnetic field. The electric force is QE, the magnetic force is QV cross B. Then, we had another equation. So I think I mentioned that this chapter is all about the balance of energy and momentum and so on and so forth. So these are, in general, in physics, they're called conservation theorems. So we had one conservation theorem already. What was that? d rho dt plus divergence of J is equal to 0. This is the continuity equation. This, if you integrate through any volume, will show that the charge contained is conserved, right? At any given time, it is conserved. This is the flow of charge. So there are no charges created. Either the charges are constant, or if there's a flow, that's because of a current that is taking it out. There's no miraculous production of charges. So this is also a conservation equation. It's referred to, of course, as a continuity equation. Okay. So now let's talk about the work done on a charge, a single charge. Well, it is F dot dl, and maybe you have to integrate it. Yeah? And there are many ways to do this. So if you have QE dot dl, let me write it this way, plus QV cross B dot dl. But so if you have a charge moving from here to here, this is V, right? But dl is also in the same direction. Well, as a matter of fact, it's too small to hold in my hand. So you can see, well, dl dt is v. Right? So that means dl is v dt. So you would have q e dot v dt plus q v cross b dot v dt. I already like this integral for many reasons. You'll see, first of all, this is a three-dimensional integral, dl. We have converted that to a single integral by going to the time variable. Another thing that we already know this, magnetic fields do not do any work on charges. So, and that's again evident here, v cross b dot v. V cross b is perpendicular to v, so this is 0. And we get q e v dt. For equations to, we can write the integral version or we can write the differential version, and they all have its, and the content is the same. So now what I can do is instead talk about the power, d dt, and I get e, let me write it this way intentionally, times qv. Right? And the integral is gone because I took the time derivative. So that is for a single charge. So if you have volume charges, QV becomes a rho V, which is J. So let me write it here for lack of a better place. QV in the 3D limit would go to rho V d tau, because Q becomes a rho d tau, not dt, d tau volume.
Okay.
Now rho times V is nothing more than J d tau. So as a result, the 3D version of this is E dot J d tau. And you'll see by a simple example, it is this term that heats up charges in a resistor. So this is also called the Joule heating term. Okay? So what I want to do is what we have done in the past. Whenever we wanted to blame everything on fields and not charges, we write charges in terms of fields. That's how we came up with energy density of the electric field and the energy density of a magnetic field. So there are two things I'm going to do. I'm going to not worry about this integral yet. We can put the integral at the very end. I just want to do good old vector calculus, because 90% of E&M, in doing just calculations, it's just vector calculus. Never mind the deep plot behind it. That you have to just work it through. So let me look at this. E dot J equals E dot. So if I look at J over here, I get two terms. I get 1 over mu 0 curl of B. And then I get mu zeros cancel, I get a minus epsilon naught dE E dot dE dt. Correct? Is everything clear? All I did was replace J with, I solve for J here. It stuck it in there. I don't have the integral anymore because I'm only computing E dot J. So nothing miraculous, okay? All right, so like I said, most of this is just vector calculus. So what I want to do is two things. First of all, I want to do this, d dt of E squared, which is E dot E, is 2 times E dE dt. Correct? I don't know. Well, if you don't believe me, it is. Yeah? So from this this term, I got a nice E squared term. By E squared, what do I mean? I mean E dot E. Okay? So if I get an E squared term, I would like to head towards a B squared term. Otherwise, things will look asymmetric. So yeah, what I'll do is look at this guy. And let's look at this quantity and use some vector calculus results. And I forgot my glasses. So I am going to turn to equation 6 on the inside cover. My writing is much bigger, so what I'm going to do is I can read this without my glasses. Have you located equation 6?
Yes.
Like the front cover of the book, or depending on your book, it might be the back cover. Yeah.
Okay, yeah, I got it.
Yeah, so I think it's equation 6, and like I said, I can read this one, B dot minus E dot curl of E. So when I look at this, and I'm not motivating anything at this point, because like I said, it is just a good bit of vector calculus. You'll see at the end, but I want to constantly remind you what it is that I'm trying to do. I got rid of this for these two. This is what we have. Now I look at this. I mean, this is this, and that's equal to what? This minus that. I'll tell you why I like this. This will be revealed very soon. Well, I'll tell you why. This is because del cross E from Faraday's law is that. So that's pretty good. If I have this, I have that. Then I'm trading this for a divergence. If there's a proper divergence term and you're doing a volume integral, I can get an area term out of it. It's a divergence theorem out of it. So I'm trying to force two things. I want to bring in this, a term symmetric to that, and then the remainder would be a divergence term. So let's hope I don't make any mistakes, and what I'm going to do is I'm going to try to rewrite this. Therefore, E dot J equals 1 over mu 0. Please make sure I'm doing this correctly. So this is the term I want to replace. So that's going to be minus, doesn't matter which order I write it in, B dot dB dt. Oh, sorry, minus dot. I'm not doing anything to this here. So what I'm doing is I'm taking this and putting it in here, mind you. So then I have this term, then I would have minus divergence of E cross B minus epsilon naught E dot dE dt. But I know how to simplify this guy. It's simply that. And similarly, this guy would be the time derivative of b squared. So now I'm going to put all of it together and compute dw dt, which is nothing more than E dot j, and I integrate that. So then I get minus epsilon naught d dt of E squared plus mu naught is below mu naught d dt of B squared. And then I have a d tau. And then what do I have? Minus 1 over mu naught, a nice divergence of E cross B. D tau. Hopefully my math is correct. And so I do another simple step. I bring out the time derivative and make it a total derivative outside the integral, because inside the integral, E is a function of x, y, and z. B is a function of x, but x, y, z, and t. B is also a function of x, y, z, and t. So when I take derivative with respect to t, it's a partial derivative. But then I'm integrating over all volume. So x, y, z is gone. So only function of t. So I can write it as a total derivative. And nice terms that we talked about. We've certainly done it, but hopefully you recall. Minus 1 over mu 0. I'm going to use the divergence theorem and write it as E cross B dot dA. So what am I doing over here? I integrated it over some volume over here. And then I use divergence theorem. I'm making it closed because it's the boundary of a volume. It's a closed area, not like a sheet of paper. It's the closed area. So this is the volume, closed area, and that is what this is signifying. So then, this is the energy density of the electromagnetic field. Remember, we had 1/2 epsilon naught E squared d tau is the energy density of the electric field. 1/2 v squared over mu 0 d tau from a couple of chapters ago is the energy density of the magnetic field. So this is the energy density. Let me write that. Minus 1 over mu 0. Oh, actually, I'm going to do that. Minus S. I'll explain what this is. Where U is the density, energy density of the electric and magnetic fields. Electric and magnetic field. And S equals 1 over mu 0 E cross B. This is called the Poynting vector, and look at how it's spelled. You know, I've never looked it up. I wonder if it's the name of someone.
I'm sure.
Yeah. And let me, hopefully I'm spelling it correctly as well. No class. P-O, yep. It's also called the Poynting theorem. So this is the result. Let me explain this physically. If you have electromagnetic fields and charges, the fields will do work on the charges. The power, the rate of doing work on the charge is equal to the rate of change of electromagnetic energy density with a negative sign. That means if the energy density of the electromagnetic field is decreasing, so minus and minus, the work is positive. If this is increasing, energy is taken away from charges. So this is a balance between work done on the charges and the energy density of the field. But what else could be there? There could be something flowing out. This is the term that calculates the remaining. So the rate of work done on charges in any volume is equal to the negative rate of change of the energy density contained in the field minus whatever is flowing out. So this can be interpreted as what? Energy per unit area per unit time. So it's the energy flux per unit time. Energy that's leaving the volume in the fields. Yeah. So like I said, we're looking for all the conservation results of electrodynamics. There'll be more.
That's just accounting for the stuff that's not accounted for in the other two.
Correct. Yeah, and that's exactly what it is, because we started with inequality and we just used vector calculus. It's just that we came on this nice formula that allows us to interpret terms properly. I want to do one special case. So let me, well, I'm going to leave this here. When no work, I don't know if this is grammatically correct, when no work is done, when work is not done.
I think it's still grammatically correct.
That's all the encouragement I need. When no work is done on the charges, we have, what is that? I can go back to the divergence form. I would get d dt of u d tau plus s dot dA equals 0, and I can bring this in, du d tau. I'm just going backwards now, plus I'm going to go back and use the divergence theorem. Divergence of s d tau equals 0. This is true for any volume. The only way that can happen is something that looks like a continuity equation. So when you don't have any charges, you get another nice continuity equation. So remember, the other one that we wrote previously with rho suggested that charges are conserved. Here, what this is saying is the electromagnetic energy is conserved. Either it's constant or it's flowing out. When no, when no work is done on charges. It's a special case of that. And so let's do an example on this Joule heating term. I think I've mentioned this before, and it's the use of this. It's going to be a time-independent equation. So this is, what is this term? S dot dA. This is energy per unit time, right? Or power. Okay, so, and this is an example problem that's worked in Griffiths. So you have a conducting wire, and it has a radius A, and it has a uniform current flowing through the wire. Remember, it's an ohmic material, J equals sigma E. Yeah? So that means J is along the direction of the current when it's a uniform current. So E is also along the direction of the current. So I want to do this boundary integral. So I would like to know what the electric and magnetic field is on the boundary of the cylinder. So if the current is going this way, I can use some color here, I would get an electric field in this direction. And the magnitude of the electric field, we already know the direction. It's uniform, it's V over L. Just potential per unit length. So, right, V is minus E dot dL. I'm just writing the magnitude. There's the direction. What about the magnetic field? We have to use Ampere's law. The current is going this way, so the magnetic field is curling this way. So over here, the magnetic field is coming out of the board. And what's the magnitude of the magnetic field? Well, it's mu 0 I over 2 pi a. This comes from Ampere's law. We've done this many times. EB dot dl is mu 0 I. So B dot dl translates to B times 2 pi a because everything is uniform. Now, the point is, which way will S point? E cross B. Which is E cross B? No, so tell me, is it into the board, out of the board, up,
Oh.
down, right, left? E cross B. You may be pointing in the right direction. Say it in words.
I mean, is this pointing down at the top?
Yeah, it's pointing. Good. So everywhere here, they're all perpendicular, so that's great. I even know how to take the cross product. So the magnitude of S
So I guess I just expected it to be opposite.
yeah. Well, if it were opposite, the charges in the wire will not be getting heated up. The resistor will not be getting heated up. So S is mu 0, just magnitude. We know the direction. E cross B, V over L, perpendicular. Oh, sorry, 1 over mu 0. Did I write that wrong? Mu 0 I over 2 pi a. That is V I. You're almost, now you know what to do. So that means S dot dA, well, it's S times area, VI over L. Again, there's no need for calculus, times the area of the cylinder, which is the circumference times the length of the cylinder. I didn't describe the L. L is length of the cylinder. And lo and behold, what do you get? So that means dW dt, the power, nothing is changing in time. So that term is 0 plus. So it's a long way to calculate the power in a, be it a resistor or a non-perfect conductor. This is using the momentum, no, the energy flux, turns out it's proportional to the momentum, of the electromagnetic field, and we still get P equals VI, freshman physics. Yeah, after the second semester of E&M. But it's good to know that all things fit consistently. The next thing I want to talk about requires a diagram, so I'll try my best to recreate what Griffiths has done. If you have the textbook, it'll help. I'm not so confident that I can draw properly, but it's still worth the attempt. See, if you have a point charge, Q, what does the electric field look like? Like this, correct? And we're going to do math shortly, but let's have a qualitative discussion. Now, suppose you have a point charge Q, but it's moving with some speed V. The electric field, we don't know how to compute it yet. This doesn't constitute There's no simple way for us to compute this. We don't have a formula for it. But so this is getting ahead, but it's good to have a diagram. Turns out it looks like this, except the electric field gets a little bunched at the top and sparing at the, so it gets a little bunched this way, and meaning the intensity is stronger here, and here you still get the electric field, fewer electric fields. I mean, lower. Yeah? That's what it looks like. Fine. That's the electric field. It's still radially outward. What happens if you have, so this is the electric field. Now suppose you have a charge, again moving this way. What does the magnetic field look like? Well, one charge does not constitute a steady state current, so we cannot use Ampere's law or Biot-Savart's law. But nonetheless, again, it's a qualitative discussion. If it were a cylindrical wire, the current, the magnetic field would be in the sort of feed direction, if you will. It'll come like this and point this way. It looks about the same, except it takes a, because it's not uniform, it takes an interesting shape. The magnetic field lines look it has a little, geometry, and further away from the charge, it beacons out. That also makes sense. I mean, things go intuitively. It's not too much of a problem. Fine. Now suppose you have two particles interacting. You have one charge, Q, moving this way. Everything about this I label 1, and another charge Q moving this way. So this is Q1 and Q2. So Q1 is going to create its own electric and magnetic field, and Q2 is going to create its own electric and magnetic field. Let's see which way they point. The electric field is easy because, again, I don't care about the magnitude. It is still radial. I'm assuming this is a constant speed, right? This Q is embedded into something and it's just moving with a constant speed. The electric field due to this one would point that way. And they're both positive, let's say, and this way. So I'm going to call this E2, the electric field on Q1 due to charge 2. And this one I'm going to call E1. Let's play the same game. Magnetic field. Which way is the magnetic field going to point on Q1? So it is, this charge is moving this way. So that means the magnetic field is what? Which way is it going to be?
Into the board on the left side.
On the left side, so coming out of the board?
Out of the board on
This side. So this would be B2.
That would be into, right? I think. I feel like that's into.
No, so look.
Oh, no. Yeah, you're right.
Yeah? And over here, what would it be? Is that clear? Ooh, let me make sure it's correct. Yeah, I think I'm correct. Okay, so let's look at the net electric force and the magnetic force. The electric force, it's a repulsion, so it's going to be F electric, right, on this charge, along the electric field. So this is also going to be along the electric field. What about the magnetic field? It is V cross B. Which is V cross B? V cross B. And over here also V cross B. So obviously made a mistake. No, sorry. This is going into the port. I wrote it wrongly. This is coming out, this is going into. Because it's on the other side. So yeah? Any problem with this?
I mean, it's going to take a little bit more thinking about it, I think.
That is true. Fair enough. Okay, let me give you the one part of it that is not a problem immediately. The electric force are equal and opposite of each other. Newton's laws. The magnetic force may be equal in magnitude, but are they opposite to each other? No. So we're confronted with a problem. Either Newton's third law is not valid for electrodynamics or something else is going on. Obviously, we want third law to be valid. Yeah? There's something else going on. Otherwise, the third law is used in conservation of momentum. If you have no notion of momentum conservation, things are just hopeless. So we wouldn't want to force anything, but naturally we would want momentum conservation or third law. So we'll work a little hard to show that momentum is indeed conserved. The point here is we have to look at the momentum of the charges and the momentum carried by the fields. And when we do, it'll be equal and opposite. So what is a problem is naturally resolved. So we need more than energy conservation, we need momentum conservation. But really, that discussion is moot. It is known that we would want momentum conservation. We could have just proceeded by this. But it is good to start with an apparent contradiction. If we don't work hard and resolve this, there's a looming problem. Okay? So what we're going to do is we're going to work towards understanding how momentum would be conserved in this sort of a relationship. Okay. So we need momentum in a field. I know what that means. It's vector calculus. Everything that you see with J and rho, we replace it with fields. Because we cannot not do that. I mean, we have no other option. So let's start again with the Lorentz force equation. And I'm going to write this in 3D. In 3D, this becomes rho E d tau plus Q times V becomes J cross B d tau. These are two integrals. Huh? Maybe I should do that. So I'm going to look at force per unit volume. It's easier to just not write the integral till the very end. Well, what does that mean? It's just this quantity. I don't know what I'm doing, but I know how to get started. Every time I see a rho and a J, I use Maxwell's equations. Yeah? So because we don't know where we're headed, let me write it as a theorem, and it's not a theorem, but so that we don't get confused in language, it's a calculation. So the claim is, and this is so that we don't forget where we are headed. Okay? I need to show that this is equal to, and you will see almost very easily, it's not difficult, it's just bookkeeping. And even after we get here, we're going to use further simplification. This is just long, but it's not really tedious. It's kind of fun. Now, this term, let me write this down and then I'll tell you. Like I said, this is only stage one of, this is what's good for the goose is good for the gander kind of thing. And everything has to look like this. And then there's a minus epsilon naught EDT E cross B. We like that because I know what E cross B is. Yeah? And then minus gradient of 1/2 epsilon naught E squared plus 1/2 mu naught B squared. So clearly, I don't think I can do the calculation today. It's a tedious calculation. I may even motivate it and skip it. I don't know entirely. But there are a couple of features that I want you to look at. This is a good term, right? That's that energy density term. This is great. This is proportional to S. I like that term. This is a little bit of a mess. And this, at least they're symmetric. But one good feature is what we have forced this symmetry. When we do the calculation, we won't get this. We won't get this term. But we threw it in there because what is divergence of B? Look at the Maxwell equation. Zero. So we just, we just threw it in there for it to look symmetric. Okay, so if you want me to, let's see if you want me to do this, but I'm not going to prove it. If I do it, I'm going to do it tomorrow. But let me tell you how this is going. I look at this guy, and I look at this guy, and I get F divergence of E right? Because rho is epsilon naught times divergence. Look, that's already the first term. That's what's going on. And then J, well, minus plus 1 over mu naught. What is J? Curl of B. Curl of B. Then cross B. And minus. The mu naught goes away, and I get epsilon naught. Minus epsilon naught yeah? Already you see we have gotten this. Now I'll tell you where we'll get this. So I have this term. I can write it as this minus that. And so from here, and look at that, there's that minus epsilon naught. This term appears. There's, of course, more terms that we have to worry about. I can even show you another term. D dt cross B plus E dB dt is minus curl of E. Yeah? Look, so this term gives rise to this term, which gives this one. And we have this term, you see that? And we have a similar term. You massage those terms till these guys appear. So Griffiths does this calculation in great detail. There's nothing more insightful to it, just vector substitution. But this is the more important point. Can you follow, read up if needed? Or do you want me to do it next time in class?
I can read it.
Yeah. So we'll begin the next class taking this expression for f for granted. It is simple vector substitution. A week after I teach this lecture, I forget the calculation. Whenever I need to, I just read it back up. It's not difficult, but it's insightful. Somebody thought initially to work it out, so you should know where it comes from. Okay, good. We'll pick it up on Monday.